Okay, so we were going through this proof. In this proof, we wanted to show that this happens, and after some manipulation, they took these forms. And now we are given that this integer a dash b also has the representation a prime dash b prime. So from our definition of equality of two integers, we get this condition, and from this condition we can easily see that these two expressions are the same, or these two natural numbers are the same, because you can replace a plus b prime with a prime plus b, and you can replace a prime plus b with a plus b prime. So that's how you can get what you want, and this ultimately proves this equation. This is true. The other two assertions can also be similarly proved, and it's very easy to see why, having gone through all these things. So we just write like this. The remaining assertions can be similarly proved, and this completes the proof of our result, which says that addition and multiplication of integers that we have defined are now actually well-defined operations. And now we address an issue which we raised previously. When we defined integers, we considered this question that 3 doesn't seem, this natural number 3 doesn't seem to be an integer, because it's not of the form a natural number dash another natural number. So that question we are now going to answer, and it goes like this. The integers of the form n dash 0, where n of course is a natural number, behave like the natural numbers n. In what sense are we saying that integers of this form behave just like n? Note that for any natural numbers n and m, we have n dash 0 plus m dash 0. If you apply the definition of addition, it will be n plus m dash 0. Also, if you take their product, then what will it be? nm plus 0 0. So that gives us nm dash n0 plus 0m. That gives us 0. Okay. Also, n dash 0 is equal to m dash 0 if and only if you apply the definition of equality, it should this is true if and only if n plus 0 is equal to m plus 0, that is if and only if n is equal to m. So you see that in place of the natural number n, if we think of this integer n minus 0, then the integers of this form behave just like their natural number counterpart, in this sense that if you add two integers, then you get one result according to the definition of integer addition. In that result you have n plus m. That result corresponds to n plus m. If you think of a function, say a function from the set of natural numbers into the set of integers, and the function is defined like this: f of n is equal to n dash 0, then the function behaves in such a manner that if you apply the if you apply the function on the individual natural numbers n and m, and then take the sum of their images, then you get something. On the other hand, you add the natural numbers in the system of natural numbers itself and then apply the function, you get that same thing. It's like two different worlds, and there is a mirror. The object on one side is a natural number and its image on the other side is this integer n minus 0. Whatever the natural numbers are doing on this side of the mirror, an exact same thing, a similar thing will happen to the images. The images will also do a similar thing. The technical term for this type of correspondence is an isomorphism, which is a term from algebra. Okay, we would say that there is an isomorphism of the system of natural numbers into the system of integers, and you can pretty much see that instead of working with the integers which look like this, you can work with the natural numbers themselves, the natural number counterparts. That is, adding these two integers to know the result of that addition, you don't have to think too much about the actual definition of integer addition or integer multiplication. It's as if you are adding n and m themselves, because you get n plus m here. Just like that, here also you don't have to think about the actual integer multiplication that we have defined. It's like adding, it's like multiplying n and m, because we are getting n m, plus these two things are equal if and only if their integer counterparts are equal. So they are corresponding in every respect. They are respecting equality, and they are also respecting the algebraic operations. This addition is like this addition, as long as you restrict yourself to integers of this form. This multiplication, which is integer multiplication, is just like natural number multiplication if we are restricting ourselves to integers of this form, and equality also behaves similarly. Okay, so we are now going to make an identification, but before that let us mention that also the mathematical term for this is that there is an isomorphism there is an isomorphism between the natural numbers n and integers of the form n dash 0. Isomorphisms are structure preserving maps. The real meaning of this will become clear when we study algebra, or you may already know about this. Okay, here we are just simply mentioning the things, although it's not very, what should I say, it's not too important for us that these systems are isomorphic. It just gives us a way of having a subsystem of the system of integers inside the system of integers that behaves exactly like the system of natural numbers. It's like this. This is our set of integers and this is our set of natural numbers. Actually, there is no intersection, or in fact n is strictly speaking not a subset of z. But because of this identification, we are identifying n with this integer. That identification allows us to recognize a subset of z where the elements look like this. These are integers, there is no doubt. For example, the integer corresponding to this natural number here would be 3-0. This is an integer because it is of that form a-b, where a and b are natural numbers. But it's not just any whimsical association that we are making here. We are observing that this association does not affect ordinary addition and multiplication of natural numbers in this sense, as if we are working with natural numbers. Okay, and also it does not affect equality. So that's why once you identify this 3 with 3-0, then after that identification you can say that n is a subset of z. But strictly speaking, what we are really saying here is that z has a subset in it which behaves in all respects like n, but that is not equal to n. Okay. At first it will seem somewhat strange and difficult to understand, but the more you work with these things, the more natural they will become. Thus, we may identify the natural numbers with the natural numbers with integers by setting this equivalence. That is, we choose to not distinguish between this integer and this natural number, and we are justified in doing that because of these facts. Okay, in place of n minus n dash 0, if I write n, in place of m dash 0 if I write m, then adding them I would ordinarily get n plus m, but that corresponds to n plus m dash 0 according to our association. So things fall in place, luckily. So that's why we can make this identification and it's justified. This does not affect our definitions of addition, multiplication, or equality. Addition or multiplication or equality. And we can in fact write since they are consistent with each other. For instance, the natural number 3 is identified with the integer 3-0 or for example 1 is identified with 1-0. Okay, so like this we will not think of them as different things, but we will treat them as the same thing. Of course, if we set n equal to n-0, then n should also be equal to every integer that is equal to n-0. For example, 1 is equal to not only 1-0 but also to 2-1, 6-5, etc. because all of them are equal to the integer 1 dash 0. So our identification actually means that we are identifying this not only with this symbol, this specific symbol, but all the symbols that are equal in as integers. Okay, so that thing also should be kept in mind. We can now define incrementation on the set of integers for any integer x. We define the increment of x to be x plus 1. Okay, so increment is something that we have already seen in the very beginning of developing the system of natural numbers. We needed it even before laying out the piano axioms. But here for the integers also we can define incrementation now with the help of the addition of integers that we already have. So see, the roles have been reversed here. Previously we used incrementation to define addition in case of natural numbers. Here however we have addition, we already have addition for integers. Using addition we can define incrementation. And keep in mind, when we are writing this 1 here, we are actually meaning this integer, because this addition is that addition between integers. So this will make sense only when both x and 1 are integers, and 1 now is an integer after this identification has been made. However, incrementation is no longer an important operation for us, because it has been superseded by the more general operation of addition, because this is only a special case of addition. You add 1 to any integer, you get its increment. By the more general operation of addition. Okay. Now the operations we have seen are addition and multiplication. Those were already there in the system of natural numbers also. But now we are going to define new operations, new basic operations in the system of integers. Now we consider some new basic operations on the integers, and the first of that is negation. negating an integer. So this is definition. Its counterpart is not available in the system of natural numbers. This is definition 414. Negation of integers. If a dash b is an integer, then its negation denoted by minus a dash b. Keep in mind that this sign is minus, but this is our dash, the longer one, and is defined as this. Minus a dash b by definition is b dash a. Note that this is also an integer because a and b are still natural numbers and it's of that form. In particular, if n equal to n dash 0, keep in mind this is not actual equality but that identification, but we will treat this as equality because it is justified. This type of identification you will come across more and more in mathematics as you go deeper and deeper. Okay, many things are not literal equality, many things are not literal subsets, but in some sense their copies are, and practically there is no difference between the actual object and its copy, in that sense that the operations are behaving in the same way or something else is behaving in the same way. So identifications are part of mathematics. Okay, and we will also in this similar way we will identify integers among the rational numbers, because as we will see when we develop the system of rational numbers, we will see that integers actually are not rational numbers, but after some such identification we will find a subset of the rational numbers whose elements behave exactly like integers. So in that sense the integers can be thought of as rational numbers or residing inside the set of rational numbers. Okay, so if this is a natural number, in fact a positive natural number, okay, this is a positive natural number, positive natural number means n is a natural number which is not equal to 0. That is the definition of positivity, is a positive natural number. Then minus n will be 0 dash n, that we already know from this definition, but this is called a negative integer. Don't write negative natural number, okay, natural numbers are not negative. Is called a negative integer. For example, five dash 3. Okay, this is an integer. Its negation will be 3 dash 5. According to our definition. One can check that this definition is well defined. Well, just like addition and multiplication, this is also an operation. For addition and multiplication, we need two integers. For negation, we need only one integer. However, it's an operation, so one should check that it is well defined. What it simply means is that if you have two integers, say x and y, of that form, say x is a dash b and y is c dash d, and it happens that they are equal, then you have to prove that their negations are also equal, because then only this definition will be well defined. Just like we proved that addition and multiplication are well defined, we have to prove negation is also well defined. And in proving this well definedness of these operations, we are actually verifying that substitution axiom. This, however, will be seen in the second exercise at the end of this section, exercise 4.1.2. Okay, now after this definition of negation and everything, negative integers, we now come to a lemma which tells us that integers are exactly what we think they are. Like what do you see in your mind when you think of integers? You think of a set like this, no? That we have 0, to the right of 0 we have all the positive integers, to the left of 0 we have all the negative integers. That's how we feel integers are, or that's how they appear on the numbered line. Now after this definition, we are in this lemma, we are going to prove that what we think of integers, they actually are like that. Even our elaborate definition allows for us to think of them in this term or in this form. So this is lemma 4.1.5. Trichotomy of integers. And the statement is this: let x be an integer, then exactly one of these three things will happen. Then exactly one of the following three statements is true. Statement A, x is 0. Oh, we did not say, did we say what is 0? We did not say what is 0, no? We can, we should have done it before. 0 is the integer that corresponds to the natural number 0, because in the set of natural numbers we have 0. So 0 according